So the requests have been pouring in, and I'm going to make what will probably be a somewhat epic video compared to the other ones that we've posted so far. But what we need to cover right now are trees, spanning trees, and Koskals Algorithm. Okay, and so those topics, I'm going to do them all in one video. If you're solid on one and need to look at the other two or whatever, you can fast forward, whatever you need to do to get the information that you need here. But each of these I'm going to break down into two parts, that you can fully understand trees with just two rules. You can fully understand spanning trees with just two rules, and you can fully understand Kruskal's algorithm with two rules. So stick with me and we will make this as absolutely simple as we possibly can. So we'll start with a tree. What are the two rules for a tree? And there really are only two rules. Rule number one, no circuits. Okay, so that's a biggie. And I guess if we're breaking it down into two rules, they're both pretty important. Second rule, a tree has to be connected. Okay, those are the only two rules. Do not worry about picking up your pencil. Do not worry about picking up your pencil. And I could say that 100 times with P-E-N-C-I-L. I just couldn't spell it correctly if I tried. Don't worry about picking up your pencil. When we talked about Euler paths, and when we talked about Hamilton paths, and Euler circuits, and Hamilton circuits, both of those required that you kept your pencil on the paper the entire time that you were drawing them. Well, I guess all four of them required that. That's not a thing with trees. As a matter of fact, for almost all kinds of trees, you are going to have to pick up your pencil. So that's not a thing. All you need to worry about is, are there circuits? If there are circuits, it's not a tree. Is it connected? If it's not connected, it's not a tree. Those are the only two rules that we have for trees. So let's look at some examples really quickly. Here are trees. I will draw some actual trees. So here's a tree. That is a tree. There are no circuits, and it's connected. Just one piece, one graph. This is a tree. There are no circuits. It is completely connected. This is a tree. There are no circuits, and it is completely connected. And I talked about this in class. One of the ways that I like to think about checking whether or not something is a tree is, if it's a tree, I could put a marble anywhere in that graph. So say I put a marble right here and then flip the graph upside down. The marble would fall out. There are no circuits to trap that marble in, okay? Put a marble here, it'll fall. Put a marble here, it'll fall. Put a marble here, it'll fall. There's nothing to trap it. There's no way if I flipped this graph around, if I rotated it around, wherever I put a marble, eventually the marble would fall out. There's nothing holding that marble in. Okay, so if these are trees, what are some things that aren't trees? Because sometimes, you know, you kind of have to see examples of things that aren't trees to really understand what is a tree. So here are some not trees. All right. So not a tree. Here's one that is not a tree. This is not a tree because it's got a circuit. That's our first rule to check for. Does it have circuits? This one has a circuit, it's not a tree. If I dropped a marble inside of here, that marble would be stuck. No matter how I twisted and turned, the marble would never fall out. That's got a circuit, it's not a tree. Here's something else that's not a tree. And I'm going to kind of put this in a box by itself. This, inside the box, is one graph. It is not a tree because it's not connected, okay? There are no circuits, but it's not connected. It's in two separate pieces, so it can't be a tree. So those are the two things that you're looking for. If you see a circuit, it's automatically not a tree. If you see a graph that's not connected, these are two different pieces, two different components, it's not a tree, okay? So that is trees in a nutshell. We'll go back and look at that definition one more time, assuming I can find it here on my desk. So for a tree, the two things you need to worry about. Trees have no circuits. Trees are connected. And do not worry about picking up your pencil when you're drawing trees. There is no way that you could draw that tree without picking up your pencil. You can trace along here, but as soon as you go up into here, you're not going to be able to do it. You can't draw this tree without picking up your pencil and crossing over things again. So do not worry about picking up your pencil when we're talking about trees. Okay, so that is what we need to know about trees. So now, the two-step rule for spanning trees. I need another sheet of paper here. I'm running out of stuff. Spanning tree. Alright. So, two rules for a spanning tree. One, it needs to be a tree. It needs to be a tree. That only makes sense. It's a spanning tree. It needs to be a tree. Okay, so here's where the definition gets a little bit trickier. It needs to reach every vertex of graph 1. Okay, Miss Stone, what the heck are you talking about? What's graph 1? We didn't draw graph 1. I wanted to give you the definition first. Now we're going to look at it. Here is graph 1. Graph 1 is not necessarily an ES. We'll just do that. A tree. Okay? I'm going to draw a graph. This is a graph we've seen before. Here is my graph. This is definitely not a tree. It's got circuits all over the place. Let me label my vertices A, B, C, and D. So if I want a spanning tree of this graph, I need something that's a tree and that reaches every vertex of graph 1. Okay, so here's graph 1, and I'm going to do the squiggly lines here. All right. If I go from A to B, I now have vertices A and B. I could go from A to C. I've got vertex C in here now. And I go down to D. I have, if we look at the squiggly lines, that's a graph that is a tree that's going from A to B, A to C, and A to D. There are no circuits, and it's connected. And it reaches every vertex of graph 1. So it takes care of vertex A, vertex B, vertex C, and vertex D. That is not the only spanning tree. Let's make another spanning tree for the same graph. So here's another copy of graph 1. A, B, C, D. I could do A to B, B to C, C to D. That squiggly graph right there, that is a tree. There are no circuits, it's connected, and it reaches every vertex of graph 1. So the spanning tree here is different from the spanning tree here. This one I was able to draw without picking up my pencil, but we don't care about that for trees. This one I couldn't draw without picking up my pencil, but we don't care about that for trees. So don't worry about whether or not you had to pick up your pencil. So these are two different spanning trees of graph 1. Just like we did when we talked about actual trees, though, I'm going to go back now and show you what are not spanning trees. Okay, so let's draw graph 1, another copy of it. Oops, here we go. Here are some things that are not spanning trees. Okay, here's my graph 1 again, exact same graph. A, B, C, D. I'm going to draw something now that is not a spanning tree. I'm going to go from A to B, and I'm going to go from A to C. That squiggly graph right there, that is a tree. It's a tree, there are no circuits, it's not connected, but it's not a spanning tree because it doesn't take care of vertex D. It would have to go to vertex D also to be a spanning tree. So in this case, it's not a spanning tree. It is a tree, but it's not a spanning tree because it doesn't reach every vertex of the graph. Here's another example of something that, oops, wrong color, something that is not a spanning tree of that same graph. Okay. A, B, C, D. Here, I'm going to go from A to B, B to C, A to C, and C to D. Does that reach every vertex of our graph? Yes, it does. Is it a tree? No, it's not. There's a big old cycle happening right here, a big old circuit. I'm sorry, using different graph theory terminology. But there's a circuit there, so it's not a tree. And our rule says for it to be a spanning tree, it needs to be a tree and it needs to reach every vertex of graph 1. This one is a tree, but it doesn't reach all the vertices. This one reaches all the vertices, but it's not a tree. So that's why these two are not spanning trees. So, last but definitely not least, we need to take a look at Kruskal's algorithm. So this is how we find spanning trees in our graphs, but a very specific kind of spanning tree. So let's talk about it. Kruskal's algorithm. All right, this only works with weighted graphs. Oops, my centering is way off there. Okay, so Kruskal's algorithm only makes sense with weighted graphs. We can't even talk about it for a graph that's not weighted. And remember that a weighted graph is just a graph that has weights assigned to the edges. So let's go ahead and draw this very familiar graph at this point. So A, B, C, and D. And I'm going to assign weights to the edges. Okay? I'm going to say edge A to B is 15, B to C is 3, C to D is 3, A to C is 10, and A to D is 5. So I've assigned weights to my edges. So here's the two-step process for Kruskal's algorithm. Step 1, list all of the weights include any doubles or triples or quadruples or whatever for that matter. Even if I've got in this graph I have 2 3s, I need to list both of them. If I had a bigger graph and I had 17 6s, I need to list all 17 6s. So make sure you include all of the edges in that list. Even if it's the same weight as something else, make sure that you include all of them, and make sure your list is ordered from least to greatest. Okay? So I'm going to go ahead and make that list right up here. So I'll put my number 1 here to show that that's the first step. I'm doing least to greatest, including all of the edges, including doubles. So that's 3, 3, 5, 10, and 15. There's my list. Least to greatest, and I included any multiple edges. Okay, step 2. Pick the lowest value edge that doesn't form a circuit. And then rinse and repeat. Okay? Oops, rinse and repeat. Got that in there. Okay, so what that means is I'm going to start with the lowest edge on my list. The lowest weight is 3. I can pick either one of those 3s, but that is an edge in my graph. That's going to be an edge in my spanning tree. Okay? And I can cross it off. I've used that edge. So now I go back and I look for the lowest value of edge that doesn't form a circuit. Well, my next choice is 3. Can I use 3? Does that cause there to be a circuit anywhere in the graph? Nope, so I can use it. It's a completely valid choice. I check it off my list. Rinse, repeat, go back, look at the edge 5. Can I use 5 without making a circuit? Absolutely. 5 is a part of my spanning tree. That right there, that edge, is a part of my spanning tree. Check it off. Okay, the edge that's weighted 10, can I include that in my spanning tree? Well, as soon as I color in that edge, I'm going to have a circuit here, so I can't use it. Can't use it. This would make a circuit. Okay, so now what's left? I've got a 15. That's the lowest one left. I check. If I colored in 15, that would make one big circuit, this ABCD circuit. So I can't color in 15. That's not part of my spanning tree. And both of those are for the same reason, because it would make a circuit. I've gone through my list. I've followed this step over and over and over again. Pick the lowest value edge that doesn't form a circuit. What's left when I am done is the least value spanning tree. Is it a tree? Yes. There are no circuits and it's connected. Is it a spanning tree? Yes. It's a tree and it reaches every vertex in the graph that we're trying to span. And in this case, it also, because of the way we picked it, is the least value spanning tree. This is the cheapest spanning tree that you could possibly do throughout this graph. And if we wanted to figure out what the cost of the tree is, or the weight of that spanning tree, we just add up the weights of the edges. So 3 plus 3 plus 5, that's 6 plus 5. The weight of that tree is 11. And if I had swapped out either of these edges, any of those edges, for either of the two that I didn't use, it would definitely be more expensive than 11. So you can kind of see that. So we'll go over this again. Kruskal's algorithm only works with weighted graphs. It doesn't work with graphs. It just doesn't even begin to make sense for graphs that don't have weights, because we need the weights to make our list. Okay? So the first thing you do, list all of the weights. and include any doubles, and make sure your list is ordered from least to greatest. So we had 3, 3, 5, 10, 15. I included my doubles, all of the weights were listed in order from least to greatest. And the second part, pick the lowest value edge that doesn't form a circuit, and then do that over and over again. So we start at the top of our list. If it doesn't form a circuit, it's part of your spanning tree. Go to the next lowest. If it doesn't form a circuit, it's part of your spanning tree. Go to the next lowest. If it doesn't form a circuit, it's part of your spanning tree. Go through the entire list, and when you're done using edges that don't form circuits, you're going to end up with the lowest weight spanning tree. And so that is trees, spanning trees, and Kruskal's algorithm. And I know it's a lengthy video, but fast forward, it kind of all goes together. I didn't want to split it up because it makes sense in one big chunk, but if you only need bits and pieces, fast forward, rewind as needed to make sure you understand what's going on.